we're going to say, hey, everybody, it is, what is it? Tuesday? Yeah, it's Tuesday, right? Yeah, Tuesday something. Is it Tuesday? Or is it Thursday? It's Tuesday. I don't know when it is. Tuesday, January 13th. What's up? Hope everybody's having a good week. Good 2026. We got the Siri bot in the house. Hello, Siri bot. Are we, Oh, I don't want to do that. Nope. Let's refresh my page here so I can verify that we are live. Things are loading. Okay, that looks good. I did not do a network test, so hopefully we're streaming okay. Looks like we're doing good. Doing good there. We got an ad coming up soon. Everything's lit up yellow. Don't know what that means. With adjustable heads up time. Yeah, I don't know what that means. We got an ad coming up soon. Always right at the start to get rid of those pre-rolls for everybody. So, yeah, let's pop over to Blue Sky and post that. Boom, and we'll just get right into it. All right, so we've got concept mail here. We did good. We did bad, and then we did good last time. We did the traffic signal was pretty bad, and then we did pretty good on our meat-based one. We had a security nightmare, sleep cubes, the capsule hotel. We did the little game console for. They're back this time asking for a lock that's based off the national ID card. Loads of privacy concerns here, not to mention the fact that a trivially clonable master key opens the lock. But a job's a job. Stayed at a sleep cube a few times. They're not too shabby. The product or service is a great way to familiarize yourself with a company. All right, let's get going on this secure thing. We got the ad running yet? All right, ad starts in 4 minutes, so we got a 4-minute head start. Card reader is an X-Bus input connected to an RFID card reader. Learn, okay, is a simple input connected to a button inside the room. Unlock is a simple output connected to an electrical strike plate. The door is first unlocked by the hotel staff using a special card, which is all nines. The user can then reprogram their lock by holding the Learn button and scanning their card. When the user scans their card again after reprogramming, the door should be unlocked. Any card other than the user's card or the hotel staff card should not unlock the door. To unlock the door, the unlock signal should be held high for 6 time units. Okay, so when we tell it to unlock, we unlock for 6 time units. That seems pretty straightforward. So we've got learn is held, and we've got a code coming in, and we learn it. Then we've got a code coming in. It comes in here, and so that should unlock it. Now we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got a 10 digit. So we're going to have to use some RAM. We're going to need RAM. The special code is all nines, so we can get by without that. It's 3, 6, yeah, it's 10. So we don't actually need to read. We don't need to store that anywhere or read it anywhere. Like if it was changeable, we could program it here, but we don't need to do that. We're good just writing. We got 2.5 minutes there. So I think one of the first things that really stands out is we probably just want to pop this over here. This feels like a good place to plop it down. We're going to plug that in there because this is just going to sleep on X0, and when we get an X0 signal, we can just add X0 because it doesn't matter what X0 is. Let's go ahead and wire it up so it stops complaining. And then we simply turn on for 6 seconds. So we'll move 100 to P1. We'll sleep for 6 time units, and we'll move 0 to P1, and we're back to waiting on our signal. Now we definitely could probably get away without a sleep, and maybe that'll bite us. Maybe it won't. We'll see. Doesn't look like it will, but yeah. There we go. So that'll unlock That'll unlock that way. Might actually be better. Well, no, because we want that to be kind of optimized, so we might be able to get away with that. The next thing is when we learn, we want to write into this thing. So if the learn signal is high, which is, we can just let's plop a big boy out here. And we're going to wire that up to data. And that's got to go into a pin. Ooh, we need card reader too. But card reader can go two places, I think, right? Because we can read the card while we're learning. And then we can read the card normally. Do we want to read the card normally? So I guess we could signal out. We could signal out maybe. So maybe we move this up. Here I go overcomplicating things already. But that's just the nature of the game. If you're not overcomplicating your solution, what are you really doing? Let's go through there. So we'll signal to somewhere else like, hey, read the card. And maybe we can we'll wire up the card that way so they can read the card. Because we'll basically need to sleep on that signal. So I guess we don't care to scan learn. We really just want to sleep on X0. And then we want to test, like test, what is it? Test equal P0. If that's on, or I guess I should say if that's not on, we'll just say if it's not on, we're going to jump back to sleeping. Or I guess we'll jump back to unlock. Just call it un. So now we need an un here. We're going to call you sleep. I don't think we probably do need that. So if it is on, then we're going to read the card into memory. So we'll move 0 to X3. Yeah, there goes our 3-minute ad break. Okay. I mean, we'll just keep going for now. Might as well. Move 0 to X3. What do we have after this? We've got we got to write the card data. So we need to move 10 to AC. And then we're going to loop our read. Let's call it read loop. Okay, so read loop is going to move X0 to X2. Sub 1, test greater than 0. Is AC greater than 0? If it is, we're going to jump back to RL. Otherwise, we're going to jump to sleep because we basically just learned the code. If we aren't learning the code, what do we need to do? We need to move 0 over X1. And that's basically it there. So we'll have a piece up here that does some work. We may not need this many connections. As a matter of fact, it looks like it's probably going to be detrimental to have this many connections, but you know, you never can be too sure because we actually need to communicate with this thing over an X node. So it's like, do we do anything here? While we're learning, we definitely don't want to unlock. I don't know. We can let's try and assume that we're never gonna get that problem, right? So we'll have that, and we can come up here to X1. That leaves X3 perfectly open to connect there. Okay. What is not connected? We don't need X1 anymore. We just need to jump back to sleep because it's going to do the same thing. This is going to also sleep on X0. And then it's going to read the card identifier. So we're going to basically say move 10 into the accumulator. Move 0 to X1. That's our address. And then we're going to like test loop, right? So we need to test. Test equal x0, is that equal to x2, which is our data value coming from here. If they're not equal, then we need to just read the rest. We've got to keep going through this, so I guess we'll move 0 to dat. This is a good one. Because if dat is 0, what do we need? We need to add 1 to dat, but we can't add to the dat. It's like we need to add over here, I guess. So actually, that's a good rate. So we could do a test equal. If accumulator is equal to 10, well, yeah. No, that's not gonna work because we need a way to reset it. And we only have a few lines of code. We got like 1, 2, 3, 4 more lines of code. We could up the cost there. Is our ad over? Our ad is over. Welcome back. If you were watching an ad. So we did a little bit of code. We read in the full number into memory, and we've got this separate flow that's going to try to read cards. Ooh, I just realized if this is going to read off, then it's going to be a problem here. Maybe what we do is we do wire that up. But that's just reading the card, right? So if we're learning, which we should be learning the whole time. So where do we write? Yeah, right there. Okay, so test equal. If we're learning, So yeah, we don't need to jump there. We're gonna move P0 into dat, and we're gonna start working here. We're gonna test equal. It doesn't matter. We can do that anyways. Yeah, and then here we're gonna test equal dat if dat's equal to 100. So we're gonna test every time, but I mean there's not really a way around it. If we're learning, we're gonna move x0 to x2. If we're not learning, we're gonna move x0 to x1. So we're gonna push it to unlocker. So that'll kind of solve that problem for us. Then we've got here, what do we need? None of these can be negative. Okay, that's great. So what we'll do is we'll sleep x0. We'll move x0 into dat. And we'll test equal, test less than 0 is dat less than 0. Because that's going to tell us if we're done. If we're done, we're going to attempt to unlock. Otherwise, we need to, we're not going to move that. We're not going to move that. Otherwise, we're going to test equal dat to x2. And if that is, we're going to add 1. Otherwise, we're going to jump back to sleep. That's sleep, right? Otherwise, we're going to jump to, and then we're going to jump to sleep. Yeah, okay. Now, we need to do another test, actually. So we've got test dat is equal to 1. We don't need that jump. Test less than. If it's less than, yeah, okay, so we're going to jump to unlock. So we do still have the unlock piece down here. And then this is, if it's equal to x2, then we jump to sleep. Yeah, we're going to jump out. All right, if we're at unlock, we're going to test equal accumulator 10. If it was equal to 10, we got all 10 right. We're going to move 0 to x3. Well, that's pretty much it. That's pretty much it. We're going to, then we've got to clear out accumulator. So move 0 into the accumulator, move 0 back to our address, which is x1. So we're kind of resetting, and then we'll jump back up to sleep. And so that's kind of our flow. We get a number, we test it, and then we go through here. We're going to assume that we're starting where we need to. Then this over here will decide where to send the number. So let's see where we're at. Let's see how we're doing so far. So we're going to step through. We are in learning mode. So we've got a signal. We're going to go through here. We're going to set that to dat. We're going to set our values, and then we're here. We're moving that into there. So we're learning. We're learning in there. Boom, boom. Boom, boom. Boom, boom. Okay, so I just realized one thing that we didn't do. Okay, so we've got a number. We moved 0 into dat. So now we're sending numbers over there. That's testing. We're counting up. We're reading our numbers in. We're reading our numbers in. And then we should be sending an unlock signal. Why did we not send an unlock signal? Let's jump back over here. Control click there so we can run straight to it. All right, now let's step through again where we're at. We're jumping through. We're jumping through. We're reading all the numbers. We got 5. We've got 0. And we've got 8. We test that. That jumps back. Ooh. Okay. So basically, yeah, we don't want to jump to sleep yet. Well, we don't want to reset either. We don't want to reset either. Oh. You know what we need to do right here when we're out? We need to add some tests here. We need to test equal dat. If dat is 0, then we need to move, what is it, -1 over x1. We need to tell it to do its job to try and unlock. That's what we're missing. What did I remove? Ooh, I don't want to remove that. Did I remove something over there? I did, right? We need to jump back to sleep. Yeah. Okay, so now if we simulate through, we're going to run ahead. Boom, 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 boom. We're going to read all these numbers in. We got 5. We got 0. We got an 8. We send that over. Bam. We got our -1. We jump down here. Then we send the signal over. That sends the unlock code. Boom. We're learning a new code. Now, one thing that we didn't process is all 9s. So that's going to be a tough one because all 9s is also going to have to signal an unlock. And how are we going to do that? How are we going to signal an all 9 unlock? Because I guess basically it's either if it's equal to the value or if it's equal to 9, I guess, right? Because we've got 10 9s. But what if, yeah, it has to be all 9s or it has to be 0. This is a tough one. This is a tough one because how do we compare? We got 2 different codes that can unlock, and we can only store one of them. We could pull out a ROM. But then we have to compare the numbers to both. So we got to kind of have like two codes. It's almost like we need to know, is it all 9s or is it not? I wonder, do we need a second one of these checkers? Like, we kind of need a second checker, really. And then have that link up here. And so what are we doing? We're moving x0 to dat, and then we move dat to x3. Right, so here we're sleeping on x1. And we need to move x1 to dat. Or I guess we just need to test equal x1. Nope, we need to move x1 to dat. Test less than dat is that less than 0. We're going to jump to unlock. Otherwise, we're going to test equal dat to 9. And if it is, we're going to add 1. Now when we do an unlock, we're going to test equal 10. Yeah. We're going to test equal to 10. If it's equal to 10, we're going to, well, actually, we're going to test equal x1 to 1. So if that's 1, what we're going to do is we're going to move 0 to x2. And then we're going to jump to sleep, which we don't have defined. And then we're going to, so let me explain this a little bit. So what we're doing is when this gets a number, we're going to compare it to the code. We're going to forward it over here, and this is going to compare it to 9. If we've got, and then this, instead of signaling 0 down here, it'll signal 1 or 0 again. So it'll send -1, just like when it gets a -1, it'll send a -1. And then it'll send an extra number that's like, I unlocked it or I didn't unlock it. And if we didn't unlock it, so 1 means that it was unlocked by the code. So we're just going to move 0 onward. And then this will jump to sleep. If it didn't unlock it, then we're going to do our own test. We're going to say, did we find 10 9s? And if we did, we're going to move 0 to x2. We're going to unlock. And I guess before we actually need to like reset, right? So we need to reset here. That's going to move 0 to the accumulator. And then that'll go back to sleep. So this will test the 9s. And then over here, we need to send that extra move. So we're moving 0 to x3. We don't want to move 0 to x3. We want to, if it's equal to 10, we want to move 1 to x3. Otherwise, actually, first we want to move -1. Move -1 to x3. Then we want to do our test. Then we test move 0 to x3. So that's whether we unlocked it or not unlocked it. Okay, so that should work for locking and learning. If we jump over here to our master code, we should... what's going on? We don't have our jump back to sleep right there. Okay. Oh, we didn't unlock. What's the problem? That should have worked. Let's double check our logic here. We want to right there, right? So we hop over there. All right, we are here. We're testing if accumulator is equal to 0. Wait, what happened? Whoop, I took a screenshot. I did not mean to take a screenshot. Let's uncontrol click that because we got in our code here. Okay. So why are you already there? First off. Okay. We don't have to move -1. Because we're already forwarding all of the values that come to this node. I forgot about that. We have this move dat to x3, so we're already forwarding all of the numbers that come here, and this sends us -1. So we're already sending that information in. Now we say, hey, we unlocked it. It looks here. It sends a 0 down. And then we jump to reset, we reset, and we wait. And then that sends a signal. We unlocked. We're learning again. So that does its thing. Okay, and then we go here. Did not mean to control click that. Okay, we should be good there. Yeah, see, that didn't unlock it. Now we're here. So we're sending our 9s in. We're moving 9 up there. And we're moving 9 over there. So that's seeing a series of 9s. This is not matching the code that we have defined. We did have one number match. We're seeing all 9s coming in so far. We've got our 10 9s. There we go. Okay, so we get our -1 over. We jump to the unlock. That sends over a 0. I didn't unlock it. So now it does its own test, and it says, yeah, I saw the code. And we're good. Boom. And that's how you do locking security. Probably, yeah, we're high. We're high, but I think we did pretty good. I mean, this is a pretty large kind of graph. We are on the tail end of lines of code. We wrote a lot of code. But I feel pretty confident in that solution. It's a pretty nice, pretty elegant solution, if I don't do say so myself. What do we got? Remember... this is the least secure security solution I've ever seen, and I've worked on voting machines. Hey, at least we did not code in that error where we might allow you through if you have a semi-matching code where you just fill in 9s for digits you don't know. Anyway, so I've talked to the scale of things. Nutter butt engines of creation like this, the ones we have here, something gigantic. Okay. I don't think we got a lot of new... Is that like our last mission then? Are we getting close? What do we have here? We've entered into an agreement to produce some deep-sea sensing equipment for a complete ocean monitoring system. Each station will have passive sonar, magnetic anomaly detection sensors, recording continuously along with the radio uplink. Just double-checking our stream stats. Looks like we're not dropping frames. We're still doing good. That's great. Am I allowed to ask who these are for? You're allowed to ask. That was the answer. You are allowed to ask. Yeah, who are these for? Oh, okay. So they're just being... Am I allowed to ask? Yes. Okay. We got a radio transmitter, and we've got... I think this is a encryption key. Sonar is a simple input connected to a passive sonar sensor. Magnetic is a simple input connected to a magnetic anomaly detector. Radio RX is a non-blocking X-bus, and radio TX is an X-bus output connected to a radio transmitter. When a data packet is received over the radio that specifies the ID number of this sensor assembly, respond with the 6 most recent sensor readings, including the current from the requested sensor, in order from oldest to most recent. Okay. So seems pretty straightforward. The ID number of the sensor assembly is stored in a secure identity chip that can be read as an X-bus input. Okay, so basically if we receive a signal that matches, we read from basically 2 memory inputs, right? So we've got sonar coming in. We've got magnetic coming in, and we get 8461. What do we got? 1 is the passive sonar sensor, and 2 is the magnetic anomaly detector. Okay, and then they'll write 1, 2, 3, 4, 5, 6 into the thing, the blah blah blah. Okay, so yeah, I'm thinking we'll probably wire 2 things up to the receiver output. So we'll probably have that up here because the transmitter, like maybe there. Because we'll have a couple things right to the output. So this is basically going to tell work to happen. These are P's, so we need some P ports coming in here. And they're going to be writing a lot of data. Like a lot of data. But the cool thing is... the cool thing is that we don't actually really care about the address on this side. Well, actually, we do care about that address. We do need that address. We do need that address to come out. So basically, these are going to be the same. Do we even need... I have 2 X ports. I've got 2 P ports. You're just writing data, so actually, we're going to get rid of one of those. What we're going to do is we're going to have magnetic come in here, and we're going to have you come over this way. There, okay, and then we can have X1 come into data there. We cannot do it that way. We are going to have to go behind. Okay, we might have to pull, well, actually, it should be fine. We can pull you in, no. Right, we do need to go this way, because we need to come, yeah, we can still come up like that. So we have an address there. Then here, we can bridge. Where's our bridge? Our handy dandy bridge can get us in. We don't need that address. We need over here, but this address will need to come out as well. Yeah. And because we're going to need access to these ports over here. So we'll probably come out like that. Maybe even up there. Okay. Now, what this is going to do is this is going to move P. What do we got? Magnetic is P0. So which one is 1? So let's keep this. Sonar is 1, so this will be sonar. And 2 is magnetic. I think can I float you anywhere? So I can just like plop you over there, and we'll just say this is sonar. And we'll take this over here, and this is magnetic. Perfect. So we're going to move P0, which is our magnetic. And that's going to go out X1. So it's going to write in there, and then we're going to move P1 to X0. And we're going to sleep 1, and that's it. Like, that's the code right there. So if we run that, we're just writing data into this thing. And the cool thing about this is as we read in, we just automatically wrap. So we literally do not have to manage that address necessarily at all. But what we do need to do is... we need to know where we're reading from, so we need to know when we're reading. This has to wire up to a lot of different things. We've got to read from data and address and data and address. So maybe let's see how complicated 1 is. All right, let's do magnetic. So we need to wire up data here and address there, and this will come through here to X2. So X3 can go up there, but how do we tell it to work? Ooh, that's a challenge, isn't it? That is a challenge, isn't it? I got a lot of components working. I feel pretty confident. We've got this down to 1 because that's really all we need. We're just storing the readings. We've got our readings. We cannot store our readings in the same RAM unit. Do they have to be so far apart? I don't think necessarily they have to be so far apart. But I don't know that they could. I mean, I guess maybe they could be closer. But I don't think that's the issue. The issue right now is we're out of exports. We need a way for this to tell this to work. And then we need a way to send signals over there to the radio transmitter. This is all exports. So, in order for it to know which X, it would have to flip. So like based on accumulator. Testing it is going to erase it. Is that going to have to be a DAT? Who knows? Already struggling with space. Like we're pretty much out of space. Like where would I even put another one of these at this point? Like if I put it there, we're tied up there where we shouldn't be. We're locked here. Well, actually we've got that, but now how do we get the addresses into it? That is a tough dilemma. We need to know, like we need to be able to read from one of these dynamically. So I need to tell like a component which has, I really need 5 exports basically. Or I guess 6. Because I need to be able to pull this address to write it into this address. And then I need to pull the data here. So I'm wondering if maybe, just maybe, just maybe, what if we have a little component sitting there that does, maybe you can't sit right there. We need X's anyways. So we've got that and we've got that, right? So now we just need to tell it, we need this to come here. Oh, but we still need to get a signal in. See, that's the tough part, right? That's the tough part. I suppose that's already going to do a chunk of logic. Let's go ahead and implement this logic. So we're basically going to sleep on x2. And then when x2 wakes up, we're going to test equal x2 equal to x3. To x3. And if it's not, we're just going to jump back to sleep because, it's not doing anything. I think we still have to read the value probably. So we probably still need to move x2 to, I guess just move x2 to the accumulator. That's fine. All right, so we jump sleep. So theoretically, if we got here, we got the right code. Right? Actually, we just do that. Yeah. So now we need to know what signal, like we send a signal from here, like to tell that to set an address, right? Give me an address, like move accumulator x0, move x0, Yeah, then I need to test equal accumulator again. Is it equal to 1? Because if it's equal to 1, that's going to be like magnetic or something. Yeah, so this really actually needs both of these to be open. They've got to connect to the readers of these things. I really wish I had like a switch. I think that's what this thing is supposed to be. Some kind of switch. I think I can read from this side, but I don't know how to program it. I think I have to manually program it. So I can't really mess with it, right? I can program it here, but I can't program it digitally. Like, I don't know. You know, let's kind of restart. Let's start fresh here. Let's play with this for a sec. So if we go up here to our X little thing here, there's nothing in the manual. If I pull up the special manual, there's nothing really in the manual about this specific component that is readable. It is all in Chinese. And I suppose theoretically, I could... that's story documents, yeah. So theoretically, I could maybe Google Translate this page. It's really unclear. Let's just see. Let's see what we get from a translate. So if I translate, this is probably not the intended way to do it. That does not look like simplified Mandarin. So if we hold the camera up there and maybe like snap a picture. All right, we translated some parts of the page. We got a multiply column, we got an input, we got an output, we got a trigger, power, data, and an addition line. What is an addition line? Sometimes we encounter situations that cannot be solved by conventional parts or normal means. For this reason, we have developed PGA 33X6, which has a flexible and powerful logical structure which can improve the operation ability of any device. Highlights: 3 simple input pin with buffers. So these are the inputs over here. 3, it didn't catch it, but I'm going to assume it's 3 outputs. 6 transitional area multiplication vertical column. 1 setting, resetting triggers with feedback and direct output capabilities. Not sure how the setting, resetting trigger is supposed to work. It has been organized with a sum of product on-off configurations so that the input can be arbitrarily mapped to the output that can replace hundreds of discrete logic gates, which is not suitable for low power applications. Interesting. So like if I just read some of these outputs, right? I think we've got like boom, boom, boom. I can't multi-select. Let's move this over, everything over 1, which means we can get rid of those, put some wiring there, and there. Pin type mismatch. Interesting. Pin type mismatch. Huh. So these are all P pins. Is that what I'm getting? Well, that stinks. I wonder if that'll show me the number that's coming out of that end. So if we were just to move, let's say like Move 101 to X0. Maybe move 101 to X0. Just do that. That's fine. What does that do for output? Is everything 0 on the output there? Pin type. Oh, pin type mismatch. Yeah, because you're P pins, right? So it doesn't look like we got any outputs right now. So if this one's on, we could like signal there and there. What is that? Oh, it's going to be either or. Okay, but those are wired up. Okay. So if this one's on and this one's on, then we want this on, right? And that worked. So what if I did that, right? Okay, that seemed to invert it. If I put one there. Interesting. Whoop. Interesting. I'm confused about what's happening here. So these are all on. That lit that up, so it flipped back. Is that because when this row is on, it flips that and highlights that? So maybe we want to turn on the second one. Like that seems to imply that it sets data. But we're getting a 100 out. Maybe that's because it's a 100 in. But like really, like just out of curiosity, let's put you away. We pull this up here. We're gonna go in there. So let's just do that. We don't need that really anymore because we're gonna do P0. So we're just gonna do a 1 there. What do we got? We got a 1. We're moving it. We're still P0. There we go. Move that on 1. We got nothing. We got nothing. Does it have to be 100? Is it just 100? It is just 100. Okay. So like I can do a bunch of ands and ors. So this is if it's off and if it's on. So if this one is on and this one's off, then we want it to be on, basically. And we can mess with that by coming in here and we can say sleep for like 5, move 100 P1, sleep for 5. And then, what was that? Gen P1 5, right? That's just gonna loop, if I recall. Okay, let's see what we're doing. So we gen for 5. Yeah. So we push 100 over there. We've got nothing coming out. We turn that on. We got nothing coming out. We turn it off. We've got one coming out. Yeah. Interesting. Okay, that doesn't help us here. I mean, it's all P ports anyways, and we want to try to optimize reading. We don't want to like listen on our P ports. We have to constantly read and check, and they maintain their value. Whereas an export is like an actual data port. You just send data over it, read data from it. P-port is like you write a value to it, it stays there until you turn it off. What else do we have that could be useful? We do have this one that looks like LG08 is a 2.1 output AND gate. 2 input, 1 output AND gate. That doesn't. There's definitely 2 outputs on there. I guess this comes in and that's true or false. Interesting. That's interesting. I am imagining these are P ports though. Yep. Those are P ports. What else do we have? We've got 2 input, 1 output OR gate, and we've got an exclusive OR gate. When measuring input, signals less than 50 are interpreted as off, while signals greater than or equal to 50 are interpreted as on. Yeah, and then that's just an inverter. So that inverts whatever the signal is. We could like basically wire up a P port. So we push 100 over here, or we push a 0, but we don't have an off, right? This one would be and I guess exclusive and. But anyways, okay, back to something actually useful. We're gonna have to simplify this somewhere. We only need the last 6. We only need the last 6 of either one, and we're only going to read from one at a time. So I'm wondering if, because we've got 7. 1, 2, 3, 4, 5, 6, 7. Yeah. So if we add 7, we can write there, and then we can subtract 7 again, and we're back here. That's our address. So let's try and trim some of this down. All right. So we're gonna move that over here. We're gonna move that over here. We won't use this. Let's get rid of that for now. Let's get rid of the bridge. All right. We've got a mess of tangles here. Let's get rid of our tangles. Come on, tangles. Let's go away. All right, we need both pins connected, so we do need to bring our pin back down there. We do need. Let's just go in the front, right? Let's go in the front there. We do need a connection to our address port, and we will need a connection to our data port. So what are we going to do? We are going to, at the beginning of the step, we're going to move X1 into the accumulator. Because that's our current address where we're at. Or I guess we should move. So 1 is passive sonar, so we're going to move sonar in there. So we're going to move P1 into X0. Then we're going to copy that address. We're going to move X1 into the accumulator. Ooh, no, we do, move X, sorry. We do actually want to capture the address before we write anything. So we're going to move X1 into the accumulator. We're going to read that address into the accumulator. We're going to move P1 into X0. Then we're going to add 7. That should pop us to the other side. And we're going to move X P0 into X0. So that'll write both of those values out. And if we just run this, we'll do that. We're writing, because we need to move the accumulator to A0. Yeah, whoop. Not A0, X1. I'm writing the port on the remote system. So we do that, and then we do that, and then we do that because we don't write it back. Then we need to sub 7 move a sub 6, right? And we're going to move ACC to X1. Then we need to test equal, I guess before we move it, test equal ACC, or I guess test greater than 7. If it's greater than 7, we need to move 0 into ACC. Then we move ACC to X1. Then we need more code. So I guess we're going to pull in a heavy hitter here. We're going to move that over there. Now we've got to wire up all these ports again. We've got our P0 right there, P1. We've got X2 can go to data. Nope, we're still going to send X1 down there. We'll send, boom. All right, X2 will go there. Okay, so X0 is now X2. X2, ooh, is it? No, that is still X1. X1, okay. Now move X2 to the accumulator. And then move the accumulator to X2. Move the accumulator to X2. And then we basically want to sleep for one step. But we need to... well, that wraps it. That wraps it. So that's fine. Okay, so we... Yeah, I mean... Seems like the thing to do. We're writing those values in there. And we should wrap back around. Ooh, what happened there? All right, right here, we read into 40. What happened? Zero, 1, 2, 3, 4, 5, 6. Yeah, okay. So if we're greater than 6, right? All right, so we do that. Boom. We're back at the top. We write our values in. Perfect. Perfect. Okay. So that gives us the logic of that. I mean, basically. Now we need to know which one we're reading from, which is going to be really simple. We're going to send a code over, and it's going to be 1 or 2, so we can subtract 1 and multiply by 7, and that'll tell us what address modification to do. We'll add that to the address. Then we just read the last 6 data points and we write those out. So I think we really only need one more unit here, where we've got the ability to plug this in up there, and then that can go there. We can then plug that in, and we can also plug this in here. Okay. All right, so we are gonna sleep on X3. When we're gonna move X3 to accumulator, because that'll be 0. I mean, or does it have to be 0? We can save a line if we move 6 in there. Yeah, let's move that to dat. Or we won't move it yet. We won't move it yet. We're going to wait to move it until we actually need to set the accumulator, because the first thing that we have to do... Nope. we have to know what we're reading. Okay, so we're going to move x0 into the accumulator. Because then we have to subtract 1, mole 7. Yeah. And then we add... See? Boom. That's a problem right there. We need to know where we're at. We need to know where we're at. All right, so we're moving the accumulator on x1. But are we moving the accumulator on x1? Yes, we're moving the accumulator on x1. We're subtracting 1. We're multiplying by 7. Actually, up here, well, we've read it in. We've got to move it to the accumulator, jump sleep. So here we can sub 1 mole 7, right? And then we move x0 to x1, and we move AC to x1. Yeah. And that's it, really. Like, that's done. We just kind of wait for that. Cool. So we just wait for that. We go down here. We sleep on x3. We don't need to multiply anymore. Actually, we move x0 to x1. We don't even need to do that. We add x0. We add the current, boom, in there. We move ACC to x1. So that goes down here. So we move ACC into move x3 into ACC. Okay, now, no, we don't want to move that into ACC. We want to move that into x1. We want to move that straight into our address. That's where we're going to start reading from. Now we're going to read 6 backwards. So this is going to be kind of weird. We're going to move 6 into accumulator, and we're going to start our read loop. We are going to move x0. Or I guess we should first test less than, test less than, because I got to read 6 backwards. How do I invert it? Do I have like a stack maybe? Do I have any stack storage? I don't have any stack storage. Crud. Because basically I've got to read backwards, but I've got 2 columns. And so I don't know, like this column resets at 7. And this column resets at 0, like it'll read over here. So it's not actually going to be less than 0. The address will be, what is that, 13, I think? So we know that our first read is always going to be valid. Yeah, our first read is always going to be valid, and then once we subtract, so if we're at 6, we pull it in, we subtract 1, we won't be at 6 anymore, and we won't be at 14 if we're at 14. Okay, actually, that's useful. All right, so we're going to move, I'll explain why it's useful in just a moment. We're going to move x0 to X2. Then we're going to move our address, move X1 into the move ACC to dat, move X1 into the accumulator because we're going to have to do some math here. So we're going to sub 1. Now, we're going to test equal if... I just realized we're not working on that logic there. So we pulled in the 6. We're at 5. That's fine. But if we pull in a 1, so test less than 0. If accumulator is less than 0, move 6 into accumulator. Test greater than... Actually, test equal accumulator 6. So the only time it should be equal to 6 is if we were at index 7 and we subtracted 1. We're going to move 13 into accumulator. Then we test less than 0, and we move 0 into the accumulator. Sorry, we move 6 into the accumulator. Then we need to move ACC to A1. To X1. Move dat to ACC. Sub 1. And we need to do more work. We don't have any more exports. Goodness gracious. This like address modification kind of sucks. It's like it'd be great if we could read into a stack. And that's what I'm saying. If we could read into a stack, that would be awesome. But we don't have a way for it to decrement or read. And it's got to be, it says specifically, respond with the 6 most recent sensor readings, including the current, from the requested sensor in order from oldest to most recent. Oh my goodness. I totally misread that. We're way overthinking this now. Yeah. So yeah. Yeah, what do we got? We need to wrap it, but yeah, that 7 will get us one of these locations. And then we need to go 6 back. So we sub 6. Sub 6. And then we move that down here. That gives us our starting address, but it's not quite our starting address. If we're less than 0, test less than... All right, so here's the rub. We're not going to sub there. We can't sub there. We need that information here. Because we need to go backwards. So we need a minimum. We need a minimum. So we need to test less than, if accumulator is less than 7, then we're going to move 1 into dat, or we're going to, oh, no, we move 0 into dat. We move 7 into dat. Okay, then we can move accumulator to A1. I guess we can move it to A1. Not A1. It's not A1. It's X1. And then I guess we can read that again. Because then we don't have to move it a second time. Okay, so we've got 0 and 7 into DAT. We need to move 6 into the accumulator. No, we need to subtract from it. That's why we're doing that. That's why we're doing that. Because now we need to sub 6. And we need to test. Test. Test less than what do I want to do here? If x1 is less than dat, if x1 is less than dat, if ACC is less than dat, so like it's like -1 or -4, we need to add 6 to it, right? No. -4. If it's at -4, that is, we're at 0, right? So if it goes -4, we want -1, -2, -3, -4. So we need to be here, 0, 1, 2, 3. So we need to be at 3. So how do we go from -4 to 3? If we add 6, then we get 2. And then we add 1. So if we were at -5, we want to get at 2. We add 6, that's 1 plus, okay. If we're at -1, then we want to end up here. So we add 6, that's 5. And then 6 puts us here, okay. Okay. And then so 7 would be like the same. That's our lower limit, right? So if we're less than 7 or 6, then we add 6, which would be 12, and we plus 1 would be 13. Okay. Okay. So if we're less than dat, we add 6. I would just add 7, right? We add 7, which puts us back around. Yeah, that makes sense. Yeah. Yeah. And then finally we move accumulator to A1. Then we can move 6 into the accumulator. It's not A1, it's X1. Oh my goodness, stop reading those port names. Then we simply move X0 to X2. We sub 1. We test greater than 0. If it is greater than 0, we jump RL. And if not, we go back to sleeping. I think we just have enough code. Wow. All right, let's go through here. All right, we got a signal. That signal, we didn't do anything with that signal. Did we write 912? Oh, snap. I've got this thing wired up backwards. Okay, we're going to have to move this over this way. Because we actually this needs to go through the translate. And the receive needs to come up here. Okay, that needs to wire up there. And this comes down here, right? Is that how we do it? That looks like the exception. We have one line of code, so like doesn't really matter. It's never sleeping, so I guess we actually don't care about that because we're always receiving a signal. So we're just gonna do that, and then at the bottom we'll put our sleep, and it just sleeps for 1 unit. So that sleeps while we're reading data. We're reading data again. We didn't match. We go here. We pull in a match. And we send that off to the accumulator. That does some quick maths. We subtract 6 from it. Boom. We write that in there, and we start reading the data. And we're sending the wrong data. How are we sending the wrong data? Sonar. Sonar is 1 and 2. So sonar P1 goes to X1. And that's 0, right? So we wrote a 1. We wanted a 1. Let me do that again. Let us do that again. Let's get there. Okay. So we read 8 4 6s that matched. We pull in a 1. We subtract 1. We multiply by 7. And then we add the current address of X0. That wrote a 13, which wrote a 13. That's not ideal. That's not ideal. We want to read this address. We don't want to catch. Well, I don't think we caught that 13, but we did update to a 13 mid kind of sequence there. So I'm wondering if maybe, just maybe, we do SL X0. Then we do that. We can't do that. X2 comes from there. That does the 1. This is the one where we want to go back to sleep. Actually, right. Right. So I'm thinking if that sends the address to tell this to do a check, then that'll wake up every sleep unit. That lets that write data and then tell this to check, which makes sense, but we have some code. Like, we don't have any code left there. We need to do that work. Sub 1 mul 7. The problem is we need. What else do we need? Let's okay, so that's gonna add x0, right? But we removed our jump to sleep. That needs to go back to sleep. We still have our test, right? So all we have to really do is we've got our test in there. Sub 1, mol 7, add x0, and then finally we only move that. We move that over there if we need to. Then we can have that be there, and then down here we move that back into the address, and then we move x2 to x3. So we move the address over there. So that lets that wake up first. And then it tells this to read. Okay, so this comes in, writes the latest data. Then it writes that there. It writes that over there. It does its thing, and then it has decided that it's going to move 0 down. Then we do that work over here. We are -6. We add 7. Then we move that into our address. And we start reading. We're going to read the wrong value because we don't wrap. Yep, we're going to read that 15. Basically, if we're at this input, right, we need to wrap, but we won't wrap. We won't wrap. Now, if I'm here, that's 1, 2, 3, and then I'm going to read, like watch. The values aren't going to line up. We're going to run out. Yeah, see, we got the wrong numbers because we're not wrapping. We're not wrapping. We've got to do more work on wrapping. We have got to wrap these addresses, which means we've got to be reading the address and wrapping it every round, not just here at the beginning. We definitely need to get the address started. The address needs to start. I can't use dat because how can I use dat as the upper limit instead? Because basically, if it's less than 7, we're writing the lower limit, so we can say if you're less than the lower limit. Because that's what we're going to do. If you're less than the lower limit, we want to add 7. If you're greater than the lower limit, they're always going to be less than the upper limit. And I can't just add 7 to dat. It's like I really just want an intermediate node that like does this math for us. Like on the address, it does the wrapping. If I didn't need to read the address of where to write the thing to, like each of those could be, like, could I have 2 inputs? If I write the address to both of them, no, because it's still The reader still needs to update the address. So 2 readers would need 1 port for the address and 1 port for data. The writer nodes need 3 ports, but then they need to signal a port over there. Because they're going to sleep. This has the same number of exports as the big one. Am I going back to 2 RAM units? I don't know that is the right solution. Yeah, because these need 2, so they only have 2 X, because I don't have enough X on there. So they would need to be 2 big ones for each side. I just gotta figure out how to wrap once I'm greater than the upper limit, right? So if it's 0, if dat is 0, then I know what the upper limit is going to be. It'd be great if I could just like wrap 7 like a mod. Like mod this number, mod 0, that's division. Modulo, I don't think I can write a modulo in values like that. So that does a test. That writes a lower limit that does another test. I mean, I think the answer really is just going to be this right here. Just one more node that's going to sleep on X0, and we're basically just going to move this logic over here, right there, and that's it, right? So it's going to sleep on X0. I don't know why we did that. We're going to move X0 into the accumulator. We're going to test if it's greater than 7, or if it's less than 7. If it's less than 7, we don't have a DAT. We can move the accumulator to X2. Okay. Then we don't need a DAT. We've got the accumulator here. I need a DAT. Okay. Can I fit a big one in here? I can put a big one there. That's a P port, though. Can I figure a way out here? I can go up and around, and I suppose I can bridge down there. That lets me move. That doesn't work. I was going to say it lets me move inside, but it actually doesn't let me do that. I can get rid of that. That lets me pull this in here like that one. Still doesn't solve any problem for me. I can bridge this over here so we can get rid of that one and we can link it up that way. Okay, so then maybe, okay, maybe we come down here with our bridge that we had earlier. This can come out like that. All right. That is still a mismatched port. So that can come down to X3, I suppose. That can go down there. Is that going to work? That is absolutely not going to work. I do need X2. I do need X2. So like, well, I guess not. We could have this come around to X3. And then we can have X3. We can ignore the fact that we're connected on X2. And then we can copy this code over here and we can dump this component now. Okay. So here we are. We're writing that into DAT. We're writing that into DAT. We are not moving that over yet. It's not data. Then we do that. We do the add 7. We move the accumulator to X3. And then we sleep again. So that comes over to X3. And then this is largely unchanged. We sleep on X3. X3 is now our address. So we move X3 to okay, so we move X3 to X1. Okay, perfect. And then over here, what we're going to do is we're going to move DAT to accumulator. We're going to add 7. That's going to be our upper limit now. And we're going to move that on X3. And then we're going to move X3 to DAT. That is our upper limit now. So if it is over our upper limit, we will wrap it. Or I guess if it's equal to, right? Because what do we got? We got 0. That's going to be 7. So we actually just need to add 6. Right? Move. So we move that to DAT. We don't need that. We move 6 into the accumulator. And then we move X0 to X2, where we sub 1. And then here we go. Yeah, we do that. If we're not, then we test greater than if X1 is greater than DAT. I don't know what to send. If it's greater than DAT, what do we send? We've got 2 digits. Oh, man. Man. We could do that to our accumulator where we have the 0 value. So we could move ACC to X3. So that's our 0 value and our upper limit. And so we could do something really dumb. That is so dumb that it's not going to work. I was gonna try to do the digit set stuff, but it's just not going to work. We've got all of this pointer manipulation over there. So we know that you are... Oh, it doesn't matter. It doesn't matter. That's our upper limit, right? You're beyond the upper limit. So we just need to subtract 6 from you. Which means we temporarily need to know what the accumulator is. And how do we know what the accumulator is? We won't know. We won't need dat anymore. So I suppose we will still need dat. We're not going to do the 3 reads. Okay, so if you're greater than dat, we simply sub 6 from the address, but we've got to read the address somewhere, which would be into the accumulator, and we got to subtract from it. The problem with checking if we're greater than... Like, if we're greater than 6, then we know we're here, but we could be here if we're reading from that side. So we can't check that. We know if we're greater than 13 that we're golden, because we can't be greater than 13 in any other scenario. As a matter of fact, actually, we are going to automatically wrap, right? So this will wrap over here. But this will wrap back to 0. So we kind of need... I mean, like over there, it's easy because we're just wrapping it automatically. And we're wrapping both. We're wrapping both pointer values. We're not wrapping one. So it's easy to test because we know what we're testing for. This one, we don't know what we're testing for. And we don't have another export to wire it to. I'm trying to, like, what am I possibly missing here? There's got to be a trick to this problem that is very obvious, and I'm missing it. I do not know what that is. I do not know what that could be. I am officially stumped at the moment. Like, I know what to do. I just don't have enough room to do it, which is the problem. This is the challenge of this game, is that I don't have the room to do the things. Why is that over there? I don't know. What do we got? What do we have? So I need some pointer manipulation. I need a reset. I could send the address over there and then send the address back. Likely unchanged in most cases. So this could go here. So that sends the address over, and then we could enter kind of a loop mode, I guess. But we need to add... We need that. An accumulator. We don't have to write that. Now we could go in our loop mode, but we have literally 3 lines of code where we've got to read the number, test the number, do more than one more thing, so that's not going to work. That is obviously not going to work. So, I mean, we could just subtract 6 from the number. If it is less than 0, it is invalid. But 6 minus 6 is 0. So it'll always be less than 7. That's the problem, is that we need to know if it started off less than 7 to add the 6 to it. I'm not sure what exactly else we could do here. It's a tough call. It is a tough call. We just don't have enough ports to use 2 readers. Like, this is 4 ports here, so that's receive, that's that. That would signal out. This is 4 X ports and a P port. We'd have to have 2 of these to do the address writing. Just because we would need to update the other address as well. Then we still need a signal over there that it's good. But we don't want to signal twice. I suppose we wouldn't be signaling twice. So maybe we do that. Maybe we try in our second here. We'll go in here. We'll clear this out because this was just testing. And without deleting our other attempt, we're gonna see what we can do here. So we've got a P0, and we already ran out of space because we need that. We need an X coming out. We need to have this here minimum. Nothing else needs to read that. We probably do need this to come in because we want this to go into that address port. We don't really want to manage that address anywhere else. So what we're going to do is we are going to move P0 into... already got it mixed up. So 0, 1, 2, 3, and what is it? It's A over here, so it's A over here. So we're moving P0 into 0, 1, X2. So it doesn't matter where we're at there. But what we're going to do is we're going to then move X3 to X0. So we're going to write that current pointer value all the way back over here. Or I guess what we should do is we should just write, we could just initialize it where we move basically like -7, right? No, 6. -6 would be -1, -2, -3, -4, -5, -6. Yeah, we want to go back -7 into X0. But then we want to add 1. So I think what we want to do is we want to move X3 into the accumulator. We want to sub 7 move accumulator into X0. That's a lot of work for that one thing. And then we got this over here where we plug that in. But look, we do not have what we need because we need to get that X needs to escape, and it cannot. We cannot have that wire through that P port because that's not correct, and of course it connects to itself. It's not going to allow that. We could maybe move the component somewhere else, like that. That is a long way in there, and we can get that out and into that address port. Now, where do we put the readers? We have to put this somewhere, and we got to put the 2 readers in there somewhere. So it's just like, it's not really, this is not a really viable solution. We don't have all the space we need. The problem is right here. We need a P port, and we need 3 X ports. We could potentially maybe cut this down, because this is really not a lot of code. So if we use a smaller unit, we put a smaller unit there, and it just writes to the data port. It just writes to the data port. That's all it needs to do. It moves P0 into X1, and it sleeps for 1. Then we can have, I suppose, we can have a duplicate of that up here, which basically does the same thing. We're going to put that over there. Where we move P0 into X1, and we sleep for 1. And like, I mean, that is viable. If we move everything over by 1 unit, we could have an X signal out. So we have another X here. We've got 1 there. It needs to read that address. So we could bring this one down here. We need to write into that address. This X could come here. So like then we could move 0 to X0. And then you can sleep on X0. And you can move X3 into the accumulator. You can sub 7. Move the accumulator into X2. And then we're done there. And like, I need this same code in another X unit that needs to receive a signal here. It needs to read from this data port, which it already cannot do. So I have no way to get that address out now. Yeah. So that's untenable. So writing into this unit is pretty simple. Writing the data is not hard. Getting the data back out is hard. It is very difficult. I can't flip it. Because something has to have enough ports on it to read the addresses. If I could just like conditionally pull an address from somewhere, which I suppose I could technically do with one of these. I could pull in this address, move forward, and I could pull in this address. Then I could pull that. So basically, if I sleep on x3, move x3, or I don't even move it, test equal x3 to 1. You know what? Actually, I don't need that comp. I don't need to read from either of those. They are going to be the same address. I do need one to like signal this to work. So if I somehow have like these over here, that's the transmit receive. If I flip that, is that helpful? Maybe that's helpful. That was a pin type mismatch. So like that tells that to work. Then we can wire this in. So bad. This is so bad. So bad. What is the problem there? Okay. That way we can have okay. Okay, so basically we're gonna sleep on x1 because that is going to move 0 to x1. We're just gonna add x1 because it doesn't matter. We're gonna test equal x0 to x2, and then we're going to move x2 into the accumulator. If it's not equal, we're going to jump back to sleep, which is up here. Then we need to signal on x3. So we need to move 0 on x3. Nope, we need to move the accumulator to x3. So that's going to tell it 1 or 2. 1 or 2 on where to read from. We could use, I mean, it's going to have to poll every unit, every round, which sucks. But we could tell it to go, oh, I just realized I can't get the addresses out now because I've got all this crammed in there. So maybe this was a bad idea, trying to cram all that in the corner. We can wire this up like we had it earlier. That can come through there. So receive can come up. Receive needs to go. This is fine. This is fine. Receive can go there because that'll go there. We don't even really need, it doesn't matter up on space there. We can get rid of all this weird wiring nonsense here. Because what we're going to do is we're going to move this over here because all we need is to move this into data. And actually, yep, actually this perfect here. This will go into data right there. Yes, so x0, and then we move 0 to x1, right? So we are signaling over here. This will sleep on x0. We're going to add x0 because we got to get rid of that. So boom. Okay, now we just need to know where to read from and what our address is going to be. So we need one person here. We need our transmit. That's our transmit. We need to read an address. We need to write an address. We need to write an address. Can I move it up? Let's put that there. And we need to write an address. And then it can't read data. Gosh darn it. It can't read data. All right. So maybe we don't start there. We're gonna need 2 of these sitting in front here. And I keep grabbing the wrong one. All right, and we're gonna pull the address out because we are gonna need the address. So basically, we're gonna, I guess, sleep on x3. We're gonna move x3 into address. Address is down here, so that's 0x1. And then we're just gonna have the same code in both of them. Then we're going to move 6 into the accumulator, and we're gonna read. We're gonna move x3. Nope, 0, 1, right? Oh, it's that's address. 0, 1, yeah, okay. So we write the address there. We're gonna move x0 to x3. We're gonna sub 1. We're gonna test greater than. If the accumulator is greater than 0, we are going to jump back to the R loop. And we're gonna do the exact same thing down here. Then we can have like our orchestrator who really just needs to read. We'll change this one to x2 for convenience, because x2 can go up there. Then the address can go here, and then x3 can go here. And this doesn't plug into it. So I've gotten those down to 1 port each. And then I need a port to transmit, and then I need a port to receive on, to like the address on. Mother son of a gun. What if I just pull the address myself, right? So we sleep on X3. We move X3 to X1. So we don't even need to do that. We are going to add X3. I mean, why not, right? We are going to move X2 into the accumulator where we sub 6, 7, sub 7, sub 6. And then we move the accumulator. Address is on bottom, so X1. Okay, so oop. I meant to cut that. We are going to modify the address. And then we're going to move X3 into the accumulator. That's going to be our counter. We need to move the address there. And then we just do our reading over X3, just like normal. And then we're going to copy this down here, except 3 is 2, 2 is 3, 3 is 2, 3 is 2. So it's reading the address. Then you will be communicating there. And you will be communicating there. Oh my word. All right, so we move the accumulator, which will be 1 over X1. Okay. We are going to sleep on X0. We're going to move X0 into dat. We are then going to move 6 into the accumulator. And we are going to move the accumulator. And then we are going to test equal dat 1. If dat is equal to 1, we need the sonar, which is X1. So we're going to move the accumulator to X1. Otherwise, we move the accumulator to X2. Then we start our read loop where we test equal dat 1. If dat is equal to 1, we are going to move X1 to X3. Otherwise, we are going to move X2 to X3. Then we're sub 1. We're going to test greater than 0. If the accumulator is greater than 0, we're going to jump back to the read loop. Okay, that's a lot. So we're reading in these values and we're writing them into separate memory units. What is not sleeping? Something isn't sleeping. This part is not sleeping. Test equal, yeah, we need to rewrite this. All right, so we're sleeping on X0. Then we're adding X0. We're testing if X2 is equal to X3. Then we're going to move X2 to the accumulator. And we're going to run off that test. If that test failed, we're going to jump back to sleep. Otherwise, we're going to move the accumulator to X1. Okay, that should be what we want to do now. That goes back to sleep. Yeah, I can tell you this one's going to be like technically wrong. But we'll look for an optimal solution when we're done here. So we're reading that in. We got a match. We write a 1 down here. That sends a 6 over there, which pulls the current address and writes it back. And then we read the 6 values out for D3. And then we're good. And we keep going. We're not at a match. We're at a match again. This one's for 2. So we send a 6 over there. That does the same thing, and that sends us back. And we read the last 6 values. Okay, so we should be good to go. That was correct. That was correct. That one's correct. Lines of code high. Production cost is high. Power usage is high. Okay, but, you know, we did it. That's going to be the last puzzle that we solve. But we are going to look for an optimal solution there. So we're going to do Shenzhen I. What do we got? Ocean monitoring system. Because I want to see what we have here. So we're going to make a new design so we can see what an optional solution looks like to this this problem. What do we have? What is going on over here? Why is the page so massive? Wow. Are we zoomed in or are we zoomed in? We are 300%. Let's go back down to 100%. Thank you. Okay. So we got that. That looks like an optimal output here. So it looks like our optimal solution, this goes here. I'm just putting some parts out right now. And we do need 1 set of RAMs. 1 set of the RAMs. I don't have any idea how this works. Nothing is wired to the address. I don't see any way that it can work. Okay, so this one goes to our transmitter. This one comes in here. This one obviously goes there. This goes here. And this goes there. And then we write some code. We gotta wait, sleep 1. We gotta move P0 to X2, move P1 to X2, test equal X0, X1, jump wait. We didn't wire that up. We wired that up. Okay, we got the jump wait in there. We gotta move X2 to null. Wow, I forgot we had null. Test equal X1 to 1. We move X2 to null. We move 6 to the accumulator. I really don't have any idea how this is going to work. Move X2 to null. Move X2 to X3. Test equal ACC1. Sub 1. Jump loop. Okay, how does this work? So we wait there. We actually skipped that first value, but I guess that's okay. So we're writing data in. We're writing data in. All right, we get to our first match. We write the data values in. We test. We move X2 is data, so we move X2 to null. And then we test if it's equal to 1. We move X2 to null. Oh, it's interleaved. It's interleaved. We have 1, 2, 3, 4, 5, 6, 7. It's interleaved basically. So I see what we're doing. Move X2, so we're pulling data out to null, which forwards the pointer. Then we move 6 in. where we move x2 to null, and we read the interleave data. Interleaving the data. I didn't even think of that. That's smart. So basically what's happened, if we go back and we do our read, right, we're writing 8 from sonar, and then we're writing 85 from magnetic, right? So sonar, magnetic, and then we're going to do the same thing. We're going to have sonar, magnetic, sonar, magnetic, sonar, magnetic. And then what's going to happen is we end up with basically 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6. We've got 7. Essentially, we'll have 7 up till we get to a match, where then we automatically skip whatever the next value is going to be, and then we test if it's equal to 1, because we're on sonar. Always we do sonar, magnetic, right? So we were on sonar, magnetic, which put us here, and then we got a match. So we went down here. So this would have been sonar. So we went down here. This would have been magnetic. 1 is supposed to be sonar. So we test equal x equals 1. And then if it is, we do another null right, which puts us right back here on our first sonar value. Then we move 6 into the accumulator. And then we move x2 to null, right? That can't be right. Maybe I missed a step here. 1 is supposed to be sonar. And the sonar values move P0. Oh, P0 is magnetic. It's magnetic sonar. I had it backwards. Yeah, so magnetic sonar. And then we got magnetic sonar, magnetic sonar, magnetic sonar, magnetic sonar, magnetic sonar. Now, we're on a magnetic space, but we do our test, and it's true. So we don't jump back to wait. We now forward the pointer, because this would be, again, we've got 1, 2, 3, 1, 2, 3, 4, 5, 6. We've got 6 data points in there. So this would have been data point 7. So we essentially need to skip some spacing here. So we forward the pointer once automatically. That would have been magnetic. Now we're on sonar. Now we test, do we want sonar? We do want sonar. So we're actually going to skip again, which is going to put us right back here on our first magnetic point. Right? That's a magnetic point, not sonar. But the first step in our loop is going to forward the pointer. So we go from magnetic to sonar, which puts us at 85. And then we simply read those values out 6 times. And once we're done, we go back to sleep and we move the values in again. And so now our oldest value is now 23, kind of technically, because we'll definitely read more than 6 values by then. We go through here, and so yeah, it works. It's pretty ingenious. I don't want to get credit for that solution. That's pretty genius. Really impressed. Didn't even think about interleaving the components there. But yeah, noticed that we did get an extra one for finishing that. So yeah, next time we'll be moving on to more of these problems. We've got 4-ish more. At least there's not a whole bunch popping in, so I think we're nearing the end. So with that, have a good Tuesday. I'll see you on Thursday, same time. Let's pop open over here. Cheers, folks.